So we've been looking at integration concepts for a function of several variables right here. We know that a function of several variables can be expressed, or graphed, I guess, as some kind of a surface that's suspended above or below the xy plane, say the surface right here. So we've talked an awful lot about what to do if we had a, say, two-dimensional region in the plane. Then we talked about the geometric shape that was bounded above by this function, below by the region, and that this shape had a well-defined volume that we could compute. But there's another kind of important shape in the plane that we could integrate over, and that would be a curve. So what would the analog be right here? So say we have some curve in the xy plane. For each point in the curve, we find their corresponding point up on the graph and connect all of these points together. And what we'd find is some kind of curve on the graph of the function itself. Now, what would the region between the curve on the graph and the curve in the plane look like? It looks something like this, a two-dimensional thing, like a sheet coiled up. We could imagine taking the sheet and unrolling it, and so we would have some kind of an area. And so a natural question might be to ask, what's the area? Specifically, the area of the region above the curve, which was this shape in the plane, but below the surface of the graph, which was this part to describe the top edge. Well, what might be the best way to approximate the area of something like this? Well, one of the things that we could do is we could imagine taking the bottom curve down here and chopping it up into pieces. And then over each one of these pieces, we would have a strip which was almost, but not quite, a rectangle. The top end would be a little bit curvy based on the graph of the function, and it would have a little bit of a warp itself because of the curvature of the graph. But the area, however, if we assumed that the top was flat as opposed to being curvy right here, then the area of this region would be nothing more than its height times the length of its bottom segment. And so we can start turning this into some kind of summation process. We would find that the surface area could be approximated by adding up all of these rectangular shapes right here. Let's say that the height of each rectangle, well, that's going to be based off of a function value at a point xi, yi. And then we're going to have a length, a small length of the segment down here on the curve. So remember that this curve actually lives in the plane itself, and I'll draw a version of it right here. So we've got this curve floating around in the two-dimensional world, and we're going to take this curve and we're going to chop it up. Now, unfortunately, the idea of chopping it up into even bits is probably a little bit difficult to do, especially if the curve is complicated. And so we're just going to call each of these segments delta S1, delta S2, delta S3, delta S4, all the way through the end right here. Why S? Well, S is a lot of times used as the letter for arc length. It's sort of a traditional choice right here. So we're talking about the length of each one of these segments. And remember, we did learn how to compute the length of one of those segments back in one of the previous topics. And so if we take the height of the rectangle times the length of the little segment across the bottom, one of these pieces right here, we would have a rectangular, an almost rectangular sheet. And if we were to add up each one of these guys for xi, yi on the curve itself, then we would have an approximation of the surface area. If we wanted to make this exact, then we would have to take a limit as the number of subdivisions tended to infinity. But since we're taking the limit of a sum of function values times small segments, that's precisely what integrals are right here. And so we've come across yet another kind of integral, what's known as a line integral. Let's define this more carefully. Let's say that f of xy is a function of two variables who is continuous, and let's say that c is some kind of plane curve. So a shape that we could draw in the plane right here. Then the integral of the function f of xy over the plane curve is going to be what we just saw before. We're going to take function values who are on the curve, multiply by the length of a segment of the curve, add those things up for each one of the points that we had on the curve, and then take a limit as the number of subdivisions tends to infinity. This limiting sum is going to be called the line integral of f over the curve c. The little differential symbol that we're going to use for this is going to be based off of this part right here, since we're adding up small segments of length, and s is the traditional symbol used to denote arc length. We're going to call this the integral of f of x, y, ds over c. Let's approximate the line integral of x plus 2y ds over the curve c if c is the portion of the circle x squared plus y squared equals 1 found in the first quadrant. So let me sort of draw a quick picture of our domain right here. So we have the circle of radius 1, and we're focusing our attention only on the part of that circle which lies in quadrant 1. Well, since the problem says to approximate this, and we don't really have any other tools right here, I'm going to go and do a Riemann sum. This integral can be approximated by adding up a number of function values at a specific point on the curve times the length of each one of my little subdivisions right here. Since I don't really have anything to work with, let's just go and take this guy and chop it up into 3 even sections right here. Notice that this would make each one of these sections 30 degrees apart from each other. That means, in particular, that the lengths of each one of these guys should be the same. You might remember that on a circle, the length of a sector is equal to the radius times the angle in radians. And so in each one of these guys, the radius is 1, the angle is pi over 6. So the length of each one of these segments will be pi over 6 units long. So in this case, all of my delta s's will be the same. Now let's go and find sample points on each one of these arcs right here. Now between 0 and 30 degrees, pretty much the only point that I could plug in manually by hand would be this point right here at the endpoint 30 degrees. On the unit circle, that would be the point root 3 over 2, comma 1/2, the sine and cosine of 30 degrees. On the second segment, I could use the point right at 45 degrees. That would be root 2 over 2, comma root 2 over 2. On the last segment, I could either go at 90 degrees or 60 degrees, and I'll pick 60 degrees just for symmetry's sake. So that would be the point 1/2, comma root 3 over 2. And so now I could go through and work out this Riemann sum. If I take my first point, root 3 over 2 1/2, and plug it into the function f, we're going to get x plus 2 times y, which will be root 3 plus 2 over 2. And then we'll multiply that by the length of the segment, which we already worked out was pi over 6. And that'll get us a grand total of pi over 12 times root 3 plus 2. If we repeat on the second point, which was the point root 2 over 2, comma root 2 over 2, plug that into f, we're going to get root 2 over 2 plus 2 root 2 over 2, x plus 2y. That will simplify to 3 root 2 over 2, which we can then multiply by the length, which was pi over 6, to come up with pi over 12 times 3 root 2. Finally, if we take the last point, which was the point 1/2, comma root 3 over 2, pi over 12 times 1 plus 2 root 3. So now that I've worked out each one of the areas of the individual pieces, we'll simply add those up. When we do that, we'll get pi over 12 times root 3 plus 2 plus 3 root 2 plus 1 plus 2 root 3, which will give us a grand total of pi over 4 times 1 plus root 2 plus root 3. If we made a crude approximation of this as being 3.14 divided by 4 times 1 plus 1.4 plus 1.7, then we would find that this is approximately equal to 3.2. Of course, there's only so much that you can do with the actual definition right here. What we need is a high-powered tool, a fundamental theorem of calculus. To build such a fundamental theorem, let's focus our attention on what one of these curves might look like. So let's suppose that we had this curve here, but let's just say that it's some random curve. It was a plane curve. That means that this curve right here could be expressed as the graph of some vector-valued function c of t, who takes the form x of t, y of t. It might be hard to find this guy, but the hypothesis is that he's out there. So let's say that this endpoint right here happens when time is equal to a, and this endpoint right here happens when time is equal to b. And imagine for a second that we were to go and take a bunch of times between these values, a t1, a t2, a t3, all the way up to time equals b. So at each one of these different times, we're going to get points along this curve. And that's essentially how we graphed these things, is by plotting points. What would the Riemann sum look like under this hypothesis? Well, imagine we were to focus on one of these chunks right here. So first off, let's take a point xi, yi. Well, this point right here has to be c of ti for some magic value. And so the first part of this formula could be replaced with f of c of ti, because that's what xi, yi is. What about the delta si term? Well, delta si is supposed to be the length of this segment right here. Well, what is the length of this? It's nothing more than the distance covered between these 2 points, from this point to this point. But distance is equal to the rate times the time. Now, when I traveled from this point to this point, this took delta ti seconds, because there's a time value right here, and then there's some second time right here. So we've traveled delta ti seconds. So this piece we could express as delta ti. What about the rate? Well, rate is another word for speed, and we know how to compute the speed of a vector-valued function. We take its derivative at a specific point. That's the vector who tells me what direction we're moving in, and its length tells me how fast we're going. And so what that means is that the delta si term, the length traveled, is approximately given by the speed at that particular point times the amount of time it took us to travel there. And so a Riemann sum would take the form of adding up f of c of ti times the magnitude of c prime, I forgot the prime, of ti, times delta ti, where we're now adding this for the ti values in the interval a, b. Now, if we go and take a limit of this, our approximations will become exact, and so this will give me a second way of describing this double integral. But the cool part about this double integral is this. We're taking the limit of a sum of expressions of this form times delta t. Well, a limit of a sum is an integral. And so the limit of this sum right here, according to the fundamental theorem of calculus from Calc 1, should be the integral of this function, f of c of t, times the magnitude of c prime of t dt, evaluated from the first time value, a, to the second time value, b. And so this becomes a formula that we can use. Let me summarize this result. If f of xy is continuous, and c of t is a differentiable vector-valued function that traces out the plane curve c from time equals a to time equals b, then we can compute the line integral of f of xy ds over the plane curve c by doing a regular Calc 1 integral. Specifically, we're going to integrate the function f of c of t times the magnitude of c prime of t dt, evaluated from t equals a to t equals b. This is sometimes called the parametrized curve formula for a line integral. So let's return to our first example, but this time let's compute the line integral x plus 2y ds over the curve c, where c is the portion of the unit circle found in quadrant 1. So in order to actually compute a line integral using our parametrized equation, the integral from a to b of f of c of t times the speed of c, the magnitude of the derivative, we have to first come up with a parametric curve, c of t, who describes this shape right here. Just like when we were doing double integrals or triple integrals, the hardest part of this kind of an integration is not actually going to be working out the integral, but going to be describing the set we're integrating over. In this case, we need to come up with a plane curve who describes this shape right here. Now, one of the things we might do is, you might notice that if we solved this for y, we would get y is equal to positive the square root of 1 minus x squared, because I'm above the x-axis right here. And so one way of describing this particular shape would be by the parametric equations x equals t and y equals 1 minus the square root of t squared. I know that these two equations describe a circle because, well, if I eliminate the parameter, x is equal to t, That means that y is equal to 1 minus x squared. It describes the right shape. What values does it describe the circle for? When would I be down here at the point 1, 0? Well, that would happen when t is equal to 1. What about when I'm up here at this point? At the point 0, 1. Well, based on my equations, that would happen when t is equal to 0. If I plug in t equals 0, I get 0, 1. And so that would suggest that I'm tracing out the circle between time equals 0 and time equals 1. And so I now have the vector-valued function I need. Specifically, c of t is equal to the vector-valued function t, comma, square root of 1 minus t squared, where t goes between 0 and 1. So now we can start working out this integral. So let's do it in small pieces. Let's first figure out what f of c of t would be. So this would be f of t, comma, the square root of 1 minus t squared. And so our formula for f is it's equal to x plus 2 times y. And so there's our formula for f of c of t. What about this bit right here, the speed function? Well, the first thing we're going to have to do is come up with the derivative. Now, the derivative, remember, is done component-wise. So we'll differentiate t with respect to t to get 1. We'll differentiate 1 minus t squared to the 1/2 power to get 1/2 times 1 minus t squared to the minus 1/2 power times the derivative of the inside, which is negative 2t. And so if we clean this up, let's see, the halves cancel, and that will get me 1 comma negative t times 1 minus t squared to the minus 1/2 power. So then we can take the magnitude of this expression, which is nothing more than the square root of the sum of the squares of the pieces. 1 squared plus t times 1 minus t squared to the minus 1/2 power squared. So let's see what that is. That's 1 plus, we're going to have t squared over the square root of 1 minus t squared squared. And so the square root and the square cancel. And we're focused on 1 plus t squared over 1 minus t squared square rooted. If we put this on the common denominator of 1 minus t squared, then we're going to have 1 minus t squared plus t squared as a numerator. Well, the t squares will cancel, and so this is going to simplify to 1 over the square root of 1 minus t squared. So now we have the two component pieces we need, f of c of t and the length of c prime of t. So let's plug this expression in for this, and this expression in for that, and see where the integral takes us. So we will integrate the function t plus 2 times the square root of 1 minus t squared quantity times 1 over 1 minus t squared. And we're going to integrate that from t goes from 0 to 1. Notice that this is the integral of a product. So if we were to simply distribute through, we're going to get the integral from 0 to 1 of t times 1 minus t squared to the minus 1/2 power. I'm already thinking ahead of prepping. Plus 2 times the square root of 1 minus t squared over that, so just 2 dt. Now that it's written as a sum, we could actually integrate these two pieces separately. The second integral is easy to work on. The integral of 2 dt is just going to be 2t. Evaluated from 0 to 1 will be 2 minus 0, or 2. On the other hand, this integral right here is an excellent candidate for u substitution. If we were to let u equal 1 minus t squared, then du would be minus 2t dt, or du over negative 2 is equal to t dt. Since we have a t dt, this integral is ready for the substitution. T dt can be replaced with negative 1/2 du. The expression in the parentheses can be replaced with u to the minus 1/2 power, and so we can integrate this. We would get negative 1/2. Integrating u to the minus 1/2 power gets me u to the 1/2 power times 2 over 1, or negative u to the 1/2 power. If we back substitute, that would be negative the square root of 1 minus t squared, which we then want to evaluate from 0 to 1. If we plug in 1, we're going to get negative the square root of 0, minus, if we plug in 0, we're going to get negative the square root of 1. And so that'll get us a grand total of 1. So the first integral gets me a 1, the second integral gets me a 2. Adding these two together, we find that the line integral is exactly 3. If we remember that our approximation was about 3.2, then this is pretty consistent. Now there is something that's worth pointing out about this. This entire process depended on our ability to find this particular curve right here. What would have happened if we came up with a different vector-valued function who gave us the exact same curve? For example, you might remember that the parametric equations x equals the cosine of t and y equals the sine of t trace out the unit circle counterclockwise starting at the point 1, 0. So at the point 1, 0, this would be time equals 0. When we get up to this top point, that happens at time equals pi over 2. And so a completely different function that traces out the exact same shape would have been the vector-valued function cosine of t, sine of t, traced out on the time interval 0 less than or equal to t less than or equal to pi over 2. How would that have changed our calculation? Would it have affected our answer any? Well, let's go and see. Let's first figure out what f of c of t would have been. F of c of t would have been f of the x value cosine of t, comma the y value sine of t. And so that would have come out to being x plus 2 times y. Cosine t plus 2 sine t. What about this expression? Well, let's first focus on the derivative. The derivative of this vector-valued function, component-wise, would be negative sine of t, comma cosine of t. And so the magnitude of this would have been the square root of the first component squared, negative sine of t squared, plus the second component squared, cosine of t squared. Now notice that when you square something, the negative sign doesn't matter. And so this is really sine of t squared plus cosine of t squared, which is exactly 1. And so in this case, the speed is exactly 1. So we could plug these two values in to this integral and see what we get. We would integrate the function cosine of t plus 2 sine t times 1 dt, where this time the time values will go from time equals 0 to time equals pi over 2, since we trace out this curve with a different set of times now. So this becomes a straight up Calc 1 integral. I don't have to worry about the 1 at all. If we integrate cosine, we're going to get sine of t. If we integrate 2 sine of t, we'll get negative 2 times the cosine of t. And then we'll evaluate this from 0 to pi over 2. So we're going to have the sine of pi over 2 minus 2 times the cosine of pi over 2 minus the sine of 0 minus 2 times the cosine of 0. Let's see. The sine of pi over 2 is 1, cosine of 90 degrees is 0, the sine of 0 is 0, and the cosine of 0 is 1. And so this gives us a grand total of 1 minus 0 minus negative 2, or 3. And that's exactly what we got last time. The previous problem shows a couple of properties of line integrals that would be worth going over right now. First, a line integral over a curve is independent of the parametrization used to compute it. So it doesn't matter what vector-valued function c of t we pick, we'll always get the same value for the line integral. Armed with this, we can prove some of the more basic properties, which by now you might be expecting. For example, the line integral of a constant times the function is equal to the constant times the line integral of the function. Or, the line integral of a sum of functions is the sum of the two line integrals. Or, the line integral over a sum of two curves. And by a sum of two curves, we just mean that there's a curve component C1 and then a connected curve component C2. That would be equal to the sum of the line integrals over the two components individually. This is sort of the analog of breaking apart your domain into smaller pieces. A special case of bullet 4 is the case when the loop is closed, which means that it connects back on itself, like a circle or an ellipse. In this case, the line integral over a closed loop can be computed using any starting point. So for example, you could assume that the loop starts here and use this to build your parametrization, or you could assume that it starts right here. And the main reason why this is true is because we could take this loop and break it up into C1 and C2. Rule 4 would say that we would get the same line integral no matter which of these two starting points we use as a breakdown. However, a special notation: in the event that C is closed, we often draw an extra circle around the integral as a visual marker that lets us know that the loop involved is closed. There's one last little thing I should point out right here. You might remember when we talked about plane curves, that plane curves were actually curves that had a shape, but also an orientation. So for example, these two objects would be different plane curves. If this curve was called C, then this curve right here is traditionally called negative C. It's the same curve, but traced in the opposite direction. How do these two line integrals relate to each other? The line integral over the curve ds and the line integral over the negative curve ds. Well, if you take a look at our previous example, the one that had the counterclockwise arc, our first parametrization parametrized it from left to right, whereas our second parametrization parametrized it from right to left. And we got the same value each time. And so that will be our fifth bullet. Specifically, that line integrals of functions are independent of the direction in which the curve is parametrized. Let's compute the closed line integral of the function x plus the square root of y, where c is the loop shown below. Notice that this loop is really kind of almost immediately broken into two pieces. There's the parabolic section that goes up, and then there's the straight line section that goes down. So using our rules of line integrals, the line integral over the closed curve could be broken apart as the line integral over the parabolic part plus the line integral over the straight line bit. And so we can break this up into two small pieces. So let's focus on this part first. Now the curve P is this parabolic section that goes from the point 0, 0 up to the point 1, 1. Since we have the equation of this curve, the equation is y equals x squared, an easy way of parametrizing this would be to set x to be the variable t, and then to simply set y to be t squared. This is a fast way of getting a parametric equation that has the same plane curve. What would be the corresponding t values? Well, at t equals 0, we would get 0, 0, and at t equals 1, we would get 1, 1. And so we have a parametrization of this section. So armed with this parametrization, we could go and compute the line integral over the curve p of the function x plus the square root of y ds. Using our formula, this is going to be f of p of t times the speed of p of t dt. And so let's just work out what each of these things are. This expression right here is simply our integrand, x plus the square root of y, where we've replaced x with t and y with t squared. So that will give us t plus the square root of t squared, or t plus t, or 2t. And so that's this piece right here. This piece right here is the speed function. Since our p function is given by t comma t squared, that tells me that the derivative of this function is going to be 1 comma 2t, which means that the speed will be the magnitude of this, which is 1 plus 4t squared. And so that will be this piece right here. And lastly, our values of t go between 0 and 1. And so if we substitute in, we're going to have the integral from 0 to 1 of 2t times 1 plus 4t squared to the 1/2 power dt. And now we're down to a regular integral. This integral right here lends itself to a u substitution. If we let u be 1 plus 4t squared, then du will be 8t dt, or 1/4 du is 2t dt. Since we have a 2t dt, we can make the substitution. 2t dt will be replaced with 1/4 du. This expression becomes u to the 1/2 power, and so if we integrate that, we'll have 1/4 times u to the 3/2 power times 2/3, which gets us a grand total of 1/6 u to the 3/2 power. If we back substitute, that's 1/6 u, which is 1 plus 4t squared, to the 3/2 power. This is evaluated from 0 to 1. So when we plug in 1, we're going to get 1/6 times 5 to the 3/2 power. When we plug in 0, we're going to have 1/6 times 1 to the 3/2 power. And so that'll give us a grand total of 5 to the 3/2 power over 6 minus 1 over 6. That takes care of the first part of our integrand. Now let's focus on the next bit. In this case, I'm letting L represent the straight line segment that goes from the point 1, 1 to 0, 0. This should be easy to parametrize because we know the parametric equations for a line. We pick a starting point on the line, say the point 1, 1, and then we pick a vector who's parallel to the line. In this case, the vector -1, -1. And so starting point plus vector times t gives us parametric equations for this particular line segment right here. Notice that if t is equal to 0, then we'll hit the starting point 1, 1. If t is equal to 1, then we'll hit the ending point. And so this means that we should keep our t values between 0 and 1. to trace out this line segment. That gives us all of the information we need to compute the line integral of x plus the square root of y ds over the straight line. We're going to go and integrate f of L of t times the speed of L of t dt, where L goes from time equals 0 to time equals 1. So let's work out these different values right here. F of L of t, that's just going to be this function where we replace x with 1 minus t and y with 1 minus t. So that would be 1 minus t plus the square root of 1 minus t. The speed, well, let's see, the vector valued function L of t is 1 minus t, comma 1 minus t, which means that the derivative of this function is going to be the vector minus 1, and so the speed of this will be the magnitude of the vector minus 1, which is root 2. And so this gives us all of the information we need to plug in. We're going to have to integrate from 0 to 1 the function 1 minus t plus 1 minus t to the 1/2 power times the square root of 2 dt. If we pull the square root of 2 out, the rest of the things can be integrated fairly easily. The integral of 1, or it will be t, the integral of t is 1/2 t squared, and the integral of 1 minus t to the 1/2 power will be negative 1 minus t to the 3/2 power times 2/3, using a basic U substitution. And we'll evaluate this from 0 to 1. So that'll get us a root 2. When we plug in 1, we'll have 1 minus 1/2 minus 2/3 times 0. When we plug in 0, we'll get 0 minus 2/3 times 1 to the 3/2 power. And so that will clean up to being root 2 times 1 minus 1/2 minus 0 minus negative 2/3, which gets us the square root of 2 times 7/6, or 7 roots 2 over 6. That gives us this second piece right here. So if we clean this up, we can put this on a common denominator to come up with 6 on the bottom. 5 to the 3/2 power would be 5 root 5 minus 1 plus 7 root 2. And so there is our line integral. Compute the line integral of z ds, where c is the line from the point 1, 2, 3 to the point 4, 5, 6 in R3. Now, before we get too much farther in this, you might go and say, wait a second, this is a curve in three-dimensional space, and this is a function necessarily of 3 variables. Can we do that? Well, the short version is, yeah. Our formula for a line integral in 2 variables makes complete sense if we think about it as a function of 3 variables, because the right-hand side is defined purely in terms of vector-valued functions. So as long as we have a vector-valued function, the right-hand side makes complete sense, which means we can define the left-hand side. Just like we had for triple integral, I lose a little bit of the geometric intuition. This is no longer measuring an area per se, but I can still compute this line integral. So let's do it. The only thing we're going to need to compute a line integral is we're going to need to come up with a vector-valued function who describes this line right here. But fortunately, we have parametric equations whose job is to do that for us. We know that there's a starting point on the line, 1, 2, 3. So as long as we can find a vector tangent to the line, we can fill in that tangent vector or parallel vector right here, and we're good to go. Well, to get from the point 1, 2, 3 to the point 4, 5, 6, let's do tip minus tail, 4, 5, 6, minus 1, 2, 3, and we would end up with 3, 3, 3. And so we now have a parametric description of this line. And that means that the vector-valued function c of t equals 1 plus 3t, 2 plus 3t, 3 plus 3t parametrizes this line segment. What values of t does it work for? Well, notice that when t is equal to 0, we get the point 1, 2, 3. And that when t is equal to 1, we'll get the point 4, 5, 6. So we have a parametrization between 0 and 1. Now let's set up our integral. First, we have the integrand, f of c of t. Now that's just our integrand function right here. So if we take the function z and we plug in our vector-valued function, well, the z component is just 3 plus 3t. And so we'll have a 3 plus 3t for this part right here. On the other hand, the speed component, if we take the derivative of this function, Well, let's see. If we differentiate the top component, we'll get a 3. If we differentiate the middle component, we'll get a 3. If we differentiate the final component, we'll get a 3. And so that means that the speed of this curve is going to be the square root of 3 squared plus 3 squared plus 3 squared. That's the square root of 27, or 3 root 3. Putting this up into the integral, we now know that we're going to integrate the function 3 plus 3t times 3 root 3 dt, and we'll integrate that between 0 and 1, which were the time limits on our parametrization. Notice that we can pull a 3 out from the first pieces, so we'll have 3 times 1 plus t times 3 root 3 dt, evaluated from 0 to 1. If we pull the constants out in front, that's 9 root 3, and that's going to leave us with the integral of 1 plus t dt, evaluated from 0 to 1. So if we integrate, we'll have t plus 1/2 t squared, evaluated from 0 to 1. Plugging in 1, we're going to get 1 plus 1. Plugging in 0, we're going to get 0. And so this will give us a grand total of 9 root 3 times 2, or 18 root 3. And so there's our three-dimensional line integral. Now, an obvious question in the previous problem was what this thing represents when we're not in R2 anymore. Well, one of the ways we could think about this is we could imagine that we have a curve in, say, two-dimensional space or three-dimensional space or any dimensional space right here. Imagine that this curve has a density at each point, kind of like we did in the other one. So maybe the curve is made out of a very dense material at this part, but the curve is made out of a less dense material at this part, and it's made out of a very, very non-dense material at this part right here. So at every single point along this curve, we will have a linear density function, which we'll call f of xy, or in this case f of xyz, or in general just f of the vector x, where this could be in the plane or in three-dimensional space. So then what would a line integral of a density function represent? Well, the formula is it's a limit of sums of things with the form f of xi times delta si. This is a linear density, so it would measure something like, say, grams per inch. This piece right here is simply the length of a small segment of the wire, so that might be measured in inches. So a linear density times a length is simply going to give us a mass right here. And so what we're doing here is we're summing up tiny sections of linear mass, how much the wire weighs. And so the limit of sums of little approximations of linear mass would be, well, the total linear mass of the object. And so this at least gives us an interpretation of what a line integral means from a physical sense right here. There's sort of a common theme about what our integrals have measured. As a very special case, if the density is uniform, then the linear mass will actually be nothing more than the length of that wire. And so we've come up with another way of articulating what the length, the arc length of a curve is it's simply the line integral of the function 1 with respect to s. And notice that if we use our formula right here, that would become 1 times the length of c prime of t dt evaluated from a to b. And so since the 1 isn't contributing, this is really just the integral of the speed function. And that coincides with what we found earlier in the semester. Suppose the density at each point xy of the elliptical segment of wire shown below is given by rho of xy equals xy grams per inch. Determine the mass of the wire. Well, so we have a bunch of little buzzwords in this particular problem. We're trying to determine a mass. We have a wire with linear density. That tells me that its mass is simply going to be the line integral over this curve of the density function rho of xy ds. So if we can come up with a parametrization, c of t, then this will just be rho of c of t times the magnitude of c prime of t dt, evaluated from some starting point to some stopping point. So, just like in triple integrals and double integrals, the key part is describing the region we want to integrate over. So how do we describe a portion of an ellipse? Well, you might remember that if we use the equations x equals cosine of t and y equals sine of t, that these parametric equations describe a circle of radius 1. That is, they describe a circle who starts at the point 1, 0 and goes counterclockwise around the origin. Fortunately, this is not quite the shape we're looking for right here. The y values do what they're supposed to do. They pass through the point 0, 1 and 0, minus 1, but this is not nearly as wide as it needs to be. It somehow needs to be 3 times longer in the x direction. And so a reasonable guess would be, well, let's multiply the x value by 3. Notice that this particular curve would start at the point 3, 0 at time equals 0, would go to the point 0, 1 at time equals pi over 2, and then, if allowed to continue, would go to the point minus 1 or minus 3, 0 at time equals pi, down to the point 0, minus 1 at time equals 3 pi over 2, and would return back to the origin at time equals 2 pi. So it certainly seems like it's tracing out this ellipse right here. And in fact, if you eliminate the parameter in these two equations, you'll find that the xy equation for this is in fact the ellipse. So what does this mean? It means that we found a parametrization of this shape. 3 cosine t, sine t will give me an ellipse. We'll trace out the section we want when time starts at 0 and goes up to pi over 2. So now that we have the parametrization, we can go through and work out all of the individual details. So for example, rho of c of t. Now our rho of xy function is the product xy. In our case, the case of the curve here, the x-coordinate is 3 times the cosine of t, the y-coordinate is sine of t. And so our rho restricted to the curve is 3 cosine t sine t. On the other hand, the derivative of our function, well, the derivative of the first component is negative 3 times the sine of t, and the derivative of the second component is cosine of t. And so if we take the speed of this function, the magnitude of the derivative, we're going to come up with the square root of quantity negative 3 sine of t squared, or 9 sine of t quantity squared, plus the quantity of cosine of t squared. That would be this component right here. And so that means that our mass can be written as the integral of 3 times the cosine of t times the sine of t times 9 sine of t quantity squared plus cosine of t quantity squared to the 1/2 power dt, where we're going to integrate from 0 to 2, or pi over 2. Let's work out this integral. Notice that we're integrating a product, and so one of our tricks to try for a product is a substitution. The only thing in parentheses is this expression right here, so we could try letting u be 9 sine of t quantity squared plus cosine of t quantity squared. If we differentiate u with respect to t, then according to the chain rule, we're going to get 18 times the sine of t times the cosine of t plus 2 times the cosine of t times negative sine of t. So du dt will end up being 18 times cosine t sine t minus 2 times cosine t sine t, which means we have a grand total of 16 cosine t sine t. If we multiply both sides by dt and divide both sides by 16, then we're going to get 1/16 du is equal to cosine t sine t dt. And this particular integral has exactly that, a cosine t sine t dt portion. So that means we can make the substitution. And let's carry that substitution up here. We're going to have the integral of cosine t sine t dt can be replaced by 1/16 du. The expression in parentheses becomes u to the 1/2 power, and don't forget that there's that 3 in front. So we're going to have 3/16 times the integral of u to the 1/2 power. That would be u to the 3/2 power times 2/3. So the 3's go into there, 2 goes into 16 8 times, and that will get us 1/8 times u to the 3/2 power, or 1/8 times the expression 9 sine of t quantity squared plus cosine of t quantity squared to the 3/2 power, evaluated from 0 to pi over 2. If we plug in pi over 2, we're going to have 9 times the sine of pi over 2 squared plus cosine pi over 2 squared to the 3/2 power. If we plug in 0, we're going to have 1/8 times 9 times the sine of 0 squared plus the cosine of 0 squared to the 3/2 power. At 90 degrees, cosine is 0 and sine is 1, whereas at 0, sine is 0 and cosine is 1. And so this will give us a grand total of 1/8 times 9 to the 3/2 power minus 1/8 times 1 to the 3/2 power. Or 27/8 minus 1/8, which is 26/8, or 13/4. And so our answer, the mass of this object, is going to be 13/4, or 3 1/4 grams.